Welcome back. In this last section of Chapter 6, we'll be talking about some more applications of logarithmic and exponential functions. So just some common models, places where we use exponential functions and where we'll need to use logarithms to help us solve our problems. One would be things where populations are exhibiting what we call exponential growth. And so if we say that there's a population showing exponential growth or obeying the law of uninhibited population growth, uninhibited meaning that there is no maximum size to the population, that the population can keep growing and growing and growing and growing in size, then we'll have a function which should follow an exponential sort of a curve. That a of t, the number of things in this population at time t, is a0, our initial amount, multiplied by e to the power of k times t, where t is time and k is what's called our growth constant. You'll notice here I say that our growth constant k has to be positive, and that's because we know that when we've got a positive growth constant, if k were positive, then as time increases, the exponent will increase, which will make e to the power of larger, which will make the entire expression larger. So if our growth constant is positive, as time increases, the population increases as well. If k were negative, on the other hand, then as t gets larger, e to the kt would get smaller and smaller. This would be something where, as time goes on, the population decreases in size, which we'll look at those sorts of things later on. Those would be cases for uninhibited decay, population decay. But here for population growth, we'll have a positive growth constant. And this measures how fast or how slow the population is growing. The larger k is, the faster the population grows. The smaller k is, the slower the population grows. And now, one thing you might have noticed about this formula that I have here is that it's very similar to the formula that we had for continuously compounded interest. For continuously compounded interest, we had an initial amount, our principal, and then we had e to the interest rate times t. And so, not a big surprise here that if we're thinking about uninhibited population growth, that a form of that is continuously compounded interest. Here, your initial amount is your principal, p, and your growth constant is the interest rate, r. So this is just one example of uninhibited population growth. Although usually when we're talking about uninhibited population growth, we're talking about things like maybe growth of bacteria in a little petri dish or something along those lines, where we're talking about actual living things growing in size, their population increasing over time. So we've got this little example here where I started off by placing 1,000 bacteria in a dish, and then an hour later I note that there are 6,500 bacteria in the dish. So we've gained some new bacteria, and here we're assuming that we're working with the model of exponential growth. We're assuming that the population demonstrates exponential growth. So we know that a of t would be our initial amount times e to the kt. And of course, we know what our initial amount is. Our initial amount is a0, is that 1,000 bacteria. So I can actually say that our equation should be 1,000 e to the kt. Now, the other fact that I have here is that an hour later, I've got 6,500 bacteria. So in other words, 1 hour later, or the amount that I have when time is 1, is 6,500. So that gives me one thing that I can use to help solve for k, my growth constant. I know that when time is equal to 1, I should have 6,500 bacteria in the dish. And so now I can use this to solve for k. I'm going to first isolate that exponential expression, so dividing both sides by 1,000, that gets me 6.5. And of course, we can rewrite this as a log, so this would be log base e, or natural log of 6.5 is equal to k. Now, one thing I just want to mention before I go any further would be, for this growth constant, I am not going to start turning it into a decimal or rounding things off now. I'll round off my final answer when I start solving word problems like how many bacteria are there after a certain amount of time. But for the growth constant itself, I don't want to start rounding that, because then that means that any answers I get using that rounded off answer will be farther away from the true value than if I had used the unrounded version. So when I write out my equation for a of t, I'm going to leave k as natural log of 6.5. So for my equation, a of t, that's 1,000 e to the k times t, natural log of 6.5 times t. And I'll leave it as natural log of 6.5 until when I've done my evaluating with my calculator. And at that point, once I have a final answer, then that I'll go ahead and round things off. Okay, so let's continue on. Part 2. We want to know how many bacteria will there be after 5 hours have passed. And now here I will find my approximate answer, because I notice here I'm told to round my answer to the nearest whole number. So I start off with what I know, which is that a of t is 1,000 e to the natural log of 6.5 times t. And what we're interested in is how many bacteria will there be after 5 hours have passed, or in other words, when t is equal to 5, the final amount is equal to what? And so now I just need to find out what is a of 5, in other words. Putting in 5 for t, couple of things just to make sure that we're doing as we're simplifying this or calculating this. Remember that natural log of 6.5 is one single entity unto itself, and that the 5 is not being multiplied by the 6.5. We are not going to be multiplying 6 times 5 and turning that into 32.5. That is not what we'll be doing. If you're evaluating this, we would be evaluating it as e to the power of, using your calculator, and then left bracket, natural log of 6.5 multiplied by 5, closing our bracket. That's how I would calculate e to the power of these two things multiplied. And I'll need to do that because, of course, when I'm doing my calculations, I want to make sure that I'm not inventing new rules for logs. I want to make sure that I'm just using things the way that they're supposed to be used. And in this case, natural log of 6.5 times 5 is the natural log itself, that whole expression, multiplied by 5. And both of those are the power of e. So e to the power of, left bracket, natural log of 6.5 times 5, right bracket. When I ran that through my calculator, I get 11,602,906.25. So that means that after 5 hours, there will be 11,602,906 bacteria in the dish. A couple of things just to mention here, and you'll notice I've left a little bit of a gap, and there's a reason for that. We'll circle back to that in just a moment. But number one, since this is a word problem, then when I give my answer, I need to give my answer as a sentence. So here the question was, how many bacteria are there after 5 hours? So I answer in terms of a sentence. After 5 hours, there will be 11,602,906 bacteria. And notice I did round my answer to the nearest whole number as requested. So good, good. The second thing to note here is one of the assumptions that we make when we're talking about uninhibited population growth. We're assuming that nothing dies during this time as well. So those original 1,000 bacteria that we started with, we're assuming that they are all still alive along with any other bacteria that were created during that 5-hour period. Of course, you know in real life that some bacteria might die during this time, so is this actually going to be the exact number of bacteria in the dish? Probably not, but that's the whole point of models. They're to give us ways of examining some sort of a system or examining some sort of a situation, and in some cases we have to make little assumptions that help simplify our calculations. And for exponential growth, one of the assumptions that helps simplify our lives is we're going to assume that we don't have to worry about things leaving or dying, and so whatever bacteria get created, they stay alive and they stay with us. So, according to that model, we have 11,602,906. Now, the last thing that I wanted to do here, which was to sort of fill in a way to simplify your calculations, which, depending on what you want to do, you could do. You can certainly run this through your calculator as it is, but you could also do a little bit of simplifying to make your life easier here, noting that here you have 5 times natural log of 6.5, which is the same thing as natural log of 6.5 to the power of 5. So really what we have here, if we were thinking about that exponent, e to the power of natural log of 6.5 to the 5, that's e to the power of natural log of 6.5 to the 5. And one of the nice things here is that if you'll remember that e and natural log, that they are inverses of each other. So e to the power of natural log, those undo each other, and what you should be left with should just be the 6.5 to the power of 5. So if you can check out, if you want to, that whether we calculate it as this, 1000 e to the power of natural log of 6.5 plus 5, or whether we calculate it as 1000 times 6.5 to the power of 5, that both of those are equivalent to our final answer of 11,602,906. So, just wanted to mention that as one way we could use our properties of logs to help simplify our calculation side of things. Of course, there's nothing wrong with running things through your calculator the way that I originally had, so if you wanted to do things that way, you certainly can. Okay, so next question, we want to know how many minutes does it take for this population to double in size? So if we are reminding ourselves here, we started out with the original amount of bacteria being 1,000. So we're imagining that the population is going to double and turn into 2,000. And we want to know what is t, what is time. So we start off with, we know a of t is 1,000, e to the natural log of 6.5 times t. And we want our final amount to be 2,000. And we just need to solve for t. So I'll divide both sides by 1,000. And I have 2 is equal to e to the power of. I can rewrite that as a log, switching the inputs and the outputs, and then solving for t. So t should be natural log of 2 divided by natural log of 6.5, which turns out to be about 0.37031. Now, we just need to pause here for a minute to go back to the beginning of the question, because when we started using our equation for uninhibited population growth, we were thinking about t, time, being measuring time in terms of hours. So when I first started off, I said t was 1. That represented this being 1 hour. So that means that all the calculations I've done since t time has been measured in terms of hours. Here, t was 5 for 5 hours having passed, and that means that the t that I've solved here is t in terms of hours, 0.37 hours. But of course, we want to have our answer in terms of minutes. And since there's 60 minutes in every hour, then I could say that those 0.37031 hours times the 60 minutes in each hour gives me 22.218 minutes. So how long does it take our population to double in size? So answer rounded to 1 decimal place. It takes 22.2 minutes for the population to double. There we go. So 22.2 minutes for the population to double. And I guess that's one little bit of work to be careful about here, is to be aware of what units are being used. Of course, time could be measured in hours, minutes, however you want to measure it. And so we have to think about how were we using time before? How was it being measured before? And so going back to the beginning, we were measuring it in hours. So for this question, if we want our answer in minutes, we'll have to take our answer in terms of hours and convert it to something in terms of minutes. All right, one more example. We've got a population of Streptococcus bacteria can double in size in approximately 45 minutes. So in other words, the doubling time, the time it takes to double, is 45 minutes. And we are assuming exponential growth here, so we'd like to find our growth constant k first and then work our way upwards. One thing to note here, that we do not know what the initial population is. Right now, the initial population is a mystery. But it doesn't really matter, because when we say that the doubling time is 45 minutes, what we're saying is that after 45 minutes, the amount that you'll have would be 2 times the original amount. And so even if we don't know what the original amount is, we can still say, well, whatever that amount is, we'll have 2 times that amount. Now, one thing we need to make a choice about right here before we do anything further is whether t is going to be measuring time in terms of minutes or hours. And that's because you've got the doubling time given as 45 minutes. So you could do this with a of t, where t is measured in terms of minutes. So it would double when t is 45. However, I've said here that I want a of t to be the size of the bacteria colony after t hours. So that means that my doubling time, instead of t being 45, which would be if it was time measured in minutes, since time is being measured in terms of hours, 45 minutes is 3/4 of an hour. So my doubling time, instead of 45 minutes, I'll say that it doubles when t is 3/4. So what do we know? We know that a of t is the initial amount, e to the kt, and we know that when time is 3/4, that we'll have double the initial amount. So this is why it doesn't really matter whether or not I know the initial amount, because for my next step, I'll be dividing both sides of the equation by that initial amount, and I'll have 2 equals e to the 3/4 times k. And I can solve for this by rewriting it as a logarithmic equation. Natural log of 2 equals 3/4 k. And so then k, our growth constant, is natural log of 2 divided by 3/4. I'm going to leave it like that. If you wanted to take it and rewrite it as 4 natural log of 2 over 3, you certainly could by, instead of dividing by that fraction, flip and multiply. If you felt like going totally wild here and bringing that 4 in as a power and rewriting it as natural log of 2 to the 4, which is 16 over 3, you could do that as well. I feel like since we're not really going to be doing a whole lot in the realm of simplification later on, we're going to be running all of our work through our calculators afterwards, it's fine to leave it looking a little bit ragged here as natural log of 2 over 3/4. I don't have to have it as nicely simplified as I might if I were leaving my answer algebraically. So natural log of 2 over 3/4, and that's good enough. Okay, so let's continue on with answering our question for part 2 here, which is, now suppose you had an initial amount of 500 Streptococcus bacteria, so 500 bacteria placed in our dish, so we know that A0 is going to be now 500. We want to know how many hours will it take for the population to reach 1 million, so we want A of t to be 1 million, and so t is what? And we're looking for this solved in terms of hours, and t is measured in terms of hours, so once we've solved for t, then we're pretty much finished. We will be taking our answer and rounding it off to 1 decimal place at the very end, so we'll do that. We have that A of t is the initial amount times e to the kt. That's our general formula that we're working with here, and we know that we want the final amount to be 1 million, the initial amount to be 500, and k, we found that that was natural log of 2 over 3/4. One other thing, just before I do any further simplification here, again, this natural log of 2 over 3/4, the 2 and the 3/4 are not being combined in any sort of a way, so if you're going to think about taking 2 and dividing it by 3/4, let's not do that. Natural log of 2, that whole thing is being divided by 3/4. There's no way to really simplify that further and make it look any better. So let's start off by first isolating our exponential expression there, dividing both sides by 500. And when you do that, 1 million divided by 500 is 2,000. So we have on the right side e to the power of natural log of 2 over 3/4 times t, and on the left side we've got 2,000. And then just rewriting this as a log, natural log of 2,000 equals natural log of 2 over 3/4 times t. And so we can solve for what t is, bringing up the 3/4, dividing by natural log of 2. And so I've got t is equal to 3/4 times natural log of 2,000 divided by natural log of 2, and that's about 8.22. So how long will it take my population to reach 1 million? It will take about 8.2 hours for the population to reach 1 million. And then there we go. And so we now have our problem with our Streptococcus bacteria solved. We found our growth constant, and then once we had our growth constant, we were able to figure out how long would it take for our population to reach 1 million. It might seem a little bit extreme that it only is taking 8 hours to reach 1 million bacteria, but don't forget that it's only taking us 45 minutes to double. So we start with 500 bacteria. After 45 minutes, you've got 1,000. then 45 minutes later 2,000, then 4,000, then 8,000, then 16,000. It really builds up speed very rapidly, so it doesn't actually take that long for you to reach 1 million. So 8.2 hours for our population to reach that size of 1 million bacteria.